I'm Emil, and this is Pasquale. We're developers at Facebook in London, and we work on mobile product infrastructure there. So making stuff fast is part of our job description. So today we're going to talk about optimizing how views on Android are drawn, specifically in concern to how fast they're drawn and performance is there. In our fabulously titled talk, Flat as a Pancake. So I'm going to lower this. OK, good. So today, we're going to optimize this view. So this view of this bird represents a typical view in an Android application. Typical in the sense it's not too simple, but it's not overly complex either. It's something which you typically see in an Android recycler view, for example. So it's not too simple, so we can still optimize this quite heavily, actually. But it's not complicated, really. It's fairly common. So before I go into how we actually optimize this view, I'm going to talk a bit about how Android draws views on a system level. And this will give you more information of kind of what we can optimize and why we're doing some of these optimizations. So first of all, the drawing process. In this demonstration, the circle represents an Android view. So when Android draws a view, it goes through a number of steps. We're going to focus on 2 steps here today, but there's many more. But there's 2 that we're interested in today, and that's creating display lists and then drawing those display lists. So display list is something that the Android system introduced together with hardware acceleration in Honeycomb. Display list is a sort of cache for your drawing operations. So when the system calls on drawing your view, it records the operations you do on the canvas and stores them in this display list object. Later, that's what creating display list is. Typically in user code, that would be the onDraw method. So later, drawing this display list is really just piping the stored OpenGL commands to the GPU. A bunch of other stuff happens, but that's system details that we won't worry about in this talk today. So what happens when you draw a view for the first time? Well, the Android view system will create a display list for that view, which means call onDraw. Then it'll draw that display list. Pretty simple. Now, some time goes by, and a frame a bit later wants to draw this view again, but nothing has changed. What happens when we try to draw this view is we'll just draw the display list. We won't create a display list as nothing has changed, so the same commands that are previously cached in a display list can be reused and redrawn. The majority of time spent here is in creating the display list. So this optimization is great and saves a lot of time when drawing, because most frames, something has not changed. So how does this apply to a more complex view hierarchy? Well, it's pretty similar, but instead we perform a traversal of the tree. So we start by creating the display list for the root, and then slowly traverse through the tree, creating display lists for all its children. Each child view here has its own display list, and this is very important. We'll touch more on it later. But each view stores its own canvas command, if you will, which it executes in onDraw in its own display list. We continue drawing this by drawing each display list one by one. A parent display list will hold references to its child display lists, much like a view hierarchy. You can think of this as a display list hierarchy. So what happens when an invalidate gets called? An invalidate gets called, if you don't know, when you change a property on a view. You can call invalidate yourself as well if you're implementing a custom view. But say you set text or set an image on a view, invalidate will be called to tell the Android system that it should be redrawn at some point before the next frame. So what we need to do is call onDraw again, which means we need to invalidate the display list, really. So the next time we draw this view hierarchy, what we do is, or what the Android system does, is it traverses the hierarchy of nodes or views in our system and checks if they have a display list. This display list was purged from the cache when invalidate was called, so it needs its display list recreated. And again, this is an expensive operation, but we only need to do it on 1 out of the 6 views in this hierarchy, or 5 views. And then it continues by drawing the cached display lists, and then finally drawing the new display list, which is cached until something else changes.
Okay, so let's see how this applies to our view, the one that we want to optimize. In this talk, we will go through 3 different implementations of this view. One will be done using just standard Android views. To implement the standard one, we just use a relative layout, not really because it's the most performant, but just because it's the flattest one. So in terms, barely draw operation, in terms of draw operation, is the fastest implementation that you can get. And then we will go through some other implementation using some more advanced techniques like using drawables instead of images, and then finally using text layout. But we will introduce this concept during the presentation, so we don't need to worry about that just now. For our performance analysis, we used an internal tool we have at Facebook that is a micro benchmark for views, basically. What we do is we create a view, we set new properties on the view many times, and we measure the drawing time through Android systraces. If you don't know what Android systrace is, it's a tool that is shipped with the Android SDK that basically tracks the execution of your Android code. What we're interested really into is the traversal, so the part where the view gets laid out and then drawn. So the first implementation, the one with standard Android views, is pretty simple to understand. I mean, we have like a container, and each box represents basically a different view. This will look something like that. We will have a relative layout, and inside we will have a bunch of image view and text views. So, I mean, again, since this is very flat, when we will go and create the display list, the root will simply call create display list on each one of these children, and then when we draw, we'll call draw display list for each one of these children. And, OK, so from our tool, we were testing on a Nexus 5, if you're interested in the device. These are the times that we were seeing. So as you can see, get display list is more expensive than drawing itself, and the total time for this is roughly 2-point-something milliseconds. Now, this number might not seem like a big deal. I mean, it's just 2 milliseconds. But you have to consider that the total time to draw a frame in Android in order not to skip any frame is 16 milliseconds. And drawing is just a part of it, really, because then there's layout, and then there's the swap buffers and other stuff that's going on, plus all your user code that might run in the UI thread. So we won't really cover a lot the layout part in this talk. Actually, we won't cover it at all. But there are like excellent talks in this room after hours that will actually go through that part. So let's see how we can actually improve this. As I showed you, we are using a bunch of image views and a bunch of text views. We could actually start saying, OK, let's start reducing the number of views. So we won't have to call create display list and draw display list for each one of them. And what we chose to start with was image views. So it turns out that Android has drawables. And as the documentation states, a drawable is an abstraction for something that can be drawn. This is like the first line in the Android documentation. So drawable is actually a very simple interface. What it doesn't really do things that Vue does, like event handling. It does not contain its own display lists. So when you create the display list of a view that draws a drawable, the display list of the view will contain the information of the draw method of the drawable. And above all, does not contain any layout or measurement logic. So it's the view that has to take care of everything. So the standard usage of drawables in Android, the one that you probably have done yourself, is backgrounds. So all backgrounds for Android are drawables. So the view has its own drawable that is a background. We'll set the bound to the drawable as the size of the view, and that's it. So let's take a deeper look at what actually the drawable offers us. So the most important methods, the one that we will care about in this presentation, are really these two, draw and set bounds. So set bounds allows you to basically position and give a size to your drawable in the context of a canvas, so in the context of your view. While draw will simply basically draw the drawable on your canvas. Now, there are many different instances of drawable, and you can write your own. For the first implementation that we're going to see, what we really needed to do was to simply use some resource drawable, because all the images were in the resources, and that will go into a bitmap drawable that is basically a drawable that draws a bitmap. So another interesting thing about drawables is that they can contain their own invalidation logic. So suppose that you have a drawable and you want to handle things like state changes, or you might even want to do animation. That's something that, for example, the system does in the progress bar. The drawable has this interface defined that is drawable callback, and this interface is actually implemented by Vue. So when you set a callback to a drawable, the drawable will have a handle to tell the view that it wants to be invalidated or that it wants to execute something at a certain point. So basically, when you call invalidate self on a drawable, the drawable will go to its callback, that is your view, and will ask to invalidate a region in the view. That is the region where the drawable is. So when we switch our image views for drawables, when we look at the view, this is what we have now. So we have one view that is a view group at the bottom that contains all the drawables, and then we have two text views that are still like views on their own, and they have their own display list and whatever. And this is the XML, how the XML might look like, and this is what the on-draw of the view looks like. So now the drawing the drawables is the responsibility of the view. So in its on-draw, the view will simply go through all the drawables and draw them. And the other thing that the view has to take care of, as I was mentioning, is setting the bounds of the drawable. So when the view is laid out, we'll take all the drawables and we'll assign them a position and a size. So it will basically do what a view group will do with its children. And I mean, this is an example. As you can see, what really happens at the end is calling set bounds on a drawable. With this implementation, our number went down quite a lot. As you can see, we are getting wins in both getDisplayList and drawDisplayList. Now, notice that drawing the same GL commands will be executed at the end. So we don't expect like huge wins on drawDisplayList. It's just that instead of drawing 6 display lists, now we're doing 3 display lists. So that's mainly where the wins are coming from. And overall, we get a 13% win that, again, might not seem a lot, but in the context of a complex application might be the difference between skipping a frame and not skipping a frame. So we are now left with a view that contains a bunch of drawables and 2 text views. And we might be tempted of saying, OK, let's do something. Since this gave me wins, let's actually draw everything inside one view and get over with. So drawing text is actually, though, a very complex thing. So if you know a bit the Canvas API, you might have noticed that Canvas contains this call that is draw text. And you might be tempted to use that because, I mean, it's drawing a text. How hard can it be? Actually, drawing a text is probably one of the most complicated things you can do, not just in Android, I mean in any UI toolkit. You have to take care of things like multi-lines, right to left. In Android, you have spannables that might have different styles for different parts of the string. And you really want to handle all of these things, right, in your application. So luckily enough, Android provides this nice API that is called text layout. And this API actually comes in 3 flavors that I will explain in a minute. So the text layout is basically handles for you all the heavy lifting of having to draw text. So you can simply create a text layout, pass in a spannable, and it will measure the text for you, given a width that you provide to the text layout, and it will give you a nice draw method that you can use to draw your text. Now, this comes in 3 flavors because there are different kind of text, really. So the boring layout is something you want to use mainly for single-line text, and of course, it comes with better performances because it doesn't really have to handle a lot of different things that you have to handle in the static layout. Static layout is normal text, really. So it supports everything, multi-line, and it's what you want to use when you have a text that does not change. So like text view uses either boring or static layout, depending on what it has to render. Dynamic layout is something that we won't really cover a lot in this talk, and it's what you use if you actually want to draw editable text. And it has a lot of stuff actually to support that. So this view now that we move to text layouts for drawing tests looks like that. So what you really have is basically just a view with everything inside. You might notice that we have a title that is a one-liner, and then we have a description that can be multi-line. So you might not really know whether your line is single line or multi-line, but you might still want to use boring layout where appropriate, because it's just more performant. Luckily, I mean, you have this utility method on boring layout where you can ask the boring layout whether the text that you want to use can be rendered as a boring layout. So what happens is you ask the boring layout whether the text can be boring. It will return you some metrics if the text can be boring. And the metrics will contain the width that that text needs to be drawn as a boring layout. So then you basically check whether you can draw the text in that width or not, and I mean, decide between the two. The API, as you can see, is quite cumbersome. It's not really nice. They have introduced a new API for text layout that uses Builder, but unfortunately it's only on newer versions. So if you want to support like older versions of Android, this is what you have to stick with. And the other thing is that text layout is not a drawable. So it doesn't really give you all the nice things of bounds and just drawing on the canvas. If you call draw on a text layout itself, it will simply draw in your canvas in position 0, 0, and that's not really what you want. So what I usually do is I wrap text layout in something I call a text drawable, and I expose methods to set bounds that will use the width and height that the text layout has calculated. And in draw, this will automatically handle the canvas translations that you need to draw the text layout in the position you want it to be drawn. So in our view example, it will basically translate the canvas to the text level, draw the text, and then retranslate the canvas back. So now our XML looks quite simple, right? I mean, it's just a view, really, so you don't really need to specify anything. And the draw method is, again, just a bunch of draw calls on all our drawables. We have the text layout wrapped in our drawable, so we can just call draw. This implementation, as you can see, is faster, like significantly faster than the original one. We are talking about a 26% win in performances. Now, consider that this is just drawing time. Like, we are getting 26% win in drawing time. If you use these instruments properly, you have seen that I had to write my own layout method. So you will also get wins in layout and measurement if you use this. But again, this is more a topic that will be discussed in the next talks. So there is another very interesting thing that you can do when you use text layouts. And I mean, this is kind of hacky, but it can be very useful in some circumstances. So as I was mentioning, drawing text is very, very complex. So what happens when you have to draw a text is that the system has to generate a glyph that basically is kind of like a texture that represents the text that you have to draw. And the glyph is dependent, of course, on the size of the text, the style, the font, and everything. So when you draw the text for the first time, this glyph is created that is put in a cache that is half a megabyte, roughly. And when then you have to draw the text again after the first time, you will have the glyph already in the cache, and the drawing will be much faster. So if you have like a very complex piece of text that you have to render and you don't want to spend 50 milliseconds drawing just the text, what you can do is you can spawn a secondary thread, draw the text, the same text layout that you're going to use in your view on a picture. Picture is a nice API in Android that basically allows you to draw on a bitmap off screen, whatever you want. It just records really the canvas commands. It's kind of like a display list before display lists were invented, and it's not really supported now in hardware accelerated stuff, but we don't really care, because what we really want is for the glyph cache to be populated. This way, when you're actually going to draw your view, the first time we saw with this technique up to 10 times fastest drawing time for text. So if you're having trouble drawing your text, this might be an option for you. So So far, we've seen a lot of optimizations and way to achieve optimizations, and we have seen like good improvements, and we might be tempted to just go and write everything custom. I mean, unfortunately, this is the real world, and this is not all rainbows and unicorns, and Emil will explain you why in a sec.
Yeah, so this was awesome. Super performant views. However, they don't do everything well. So let me start with an example of where they don't do drawing well, which is contradictory to what we've said, but not really, and you'll see why. So a very important aspect of Drawables is that in contrast to views, they don't actually, or they do actually invalidate their parent when they invalidate themselves. So as Pasquale was mentioning, there are these drawable callbacks which are implemented by views, which when a drawable calls invalidate, or its method is called invalidate self, it will really just invalidate its view that it's hosted in. So this means when you're invalidating a small drawable inside a big view, the big view will be invalidated. So let's go through that with a similar diagram to before. Here I've introduced a square representing drawables. Circles are still views. So what happens? Well, when we draw this hierarchy of a root view, a view group with one child and two drawables, it could be a frame layout with one child, a background, and a foreground drawable, for example. Now what happens when we create the display list of the root? Well, draw gets called on both the drawables. They are essentially part of the view as far as the system sees drawing operations. There are no drawables. They're just part of the drawing operations on the view. So they get executed together. Now we continue and we create the display list of the child. And then we execute the display lists. Again, the drawables were part of their host's display list. Now, what happens when we call invalidate self on this view? Say it's an image and we change the icon. Well, it invalidates this host, meaning next time we draw this hierarchy, we will need to recreate the display list of the host. This involves calling draw on both those drawables. This is very bad because it was only one of the drawables that really needed to be redrawn. But given that it's part of a view, the view needs to redraw everything. That includes what we can in this diagram see as child drawables, but the system doesn't see them as children as much as the same thing in the display list sense. So as you can see, we then draw the display lists, and we don't need to create a new display list for the child view because it has its own display lists and drawables do not. So what instead happens when we invalidate the view? Let's see why this is more performant. When we try to draw this hierarchy again, and remember now the child view has changed some aspect of it, triggering an invalidate call. We only need to create the display list for that one view because that was the only display list being invalidated. And here we can just reuse the display list and the drawing commands from both those other drawables next time we need to draw that display list. And then we go on and draw the last display list. So I'm going to show you an example with this example view, which illustrates when this can cause really bad performance, or fairly bad performance at least. Say you have this button here, which, say you're using the material ripple drawable. A ripple drawable has a great animation, and it looks super smooth because it calls invalidate on every frame for the whole animation. So this will be invalidated for, I don't know, half a second, something like that, while the ripple ripples out. This means if everything is a drawable, the text needs to be re-rendered. And, well, everything needs to be re-rendered, but this text specifically. Text is cumbersome to draw, and that makes it very, very expensive. It is definitely the most expensive drawing operation in a typical Android app. So typically you do not want your text to be redrawn when your text has not changed. We took some measurements on this by using the framework Pasquale described before, but just invalidating this tiny button and seeing the performance. So because we're invalidating the smaller area and things are cached, the numbers here are a lot lower than before, but we really just care about the relative numbers. So you can see here that the standard version, which is the relative layout version, is by far the best performing view because all the display lists are there. We have display lists for every individual element, meaning that if you invalidate one of the elements, that invalidation isn't propagated to the rest of the drawable elements. All the invalidations are really just confined to that space where they need to invalidate. Drawable images isn't actually that bad because, well, the drawing images isn't really that hard. So it doesn't matter as much that we're redrawing those images. Where it gets really bad, though, is when we put the text in Drawables. Because then we take out the text display lists and practically merge them up into the root. So the text display lists are part of the root display lists. So when we're pressing that button and that ripples out in 60 frames per second, we're going to be redrawing the text every frame. And this is what hurts that performance of the text so much. So what can you do to get the performance gains Pasquale talked about, but avoid these kinds of things? Well, it's really all about the context of your application. But one pretty simple thing is to look at views which have these frequent invalidations, or in our case, drawables that have this frequent invalidation, and move them from being drawables. Pretty much don't do the optimizations we talked about, leave them as views. Because if that one button was a view, its invalidations wouldn't actually trigger a redraw of any text. It would not trigger a redraw of anything else than the button. So something to do is locate the things that invalidate often and confine the invalidation to as small area as possible. And this can easily be done by just not using a drawable, but using a view for those drawing operations instead. Also, there's always the trade-off. If, for example, you have this fully flat view and that makes scrolling impeccable, that might be worth it doing it if, for example, you skip a frame when pressing a button. That might not be as noticeable to the user. So it's all about trade-offs, the context of your application, and really just testing and seeing how it works. There are other limitations of this, or I shouldn't say limitations, but things to consider before performing these optimizations. Accessibility, namely. So accessibility is highly important. And I jumbled RTL into this, but they are kind of on the same point. So accessibility is very important, and the Android framework actually does a great job handling both accessibility for like screen readers and such things, as well as right-to-left layouts. It does this for you and implements this based on views. All you really need to do is add content description to images and make sure your strings are translated properly and such things. But with doing everything yourself, the Android view system doesn't actually know that the text in the view is text or the image in the view is a button. It sees everything as a view hierarchy, so all it sees is a flat custom view. It knows nothing about this view. So it's not too bad, actually. The Android APIs exist for creating what's referenced to as virtual views. And this is done via the accessibility node provider, but it's nothing I'll go into here. It's possible. It's cumbersome, but it's definitely possible. So again, trade-offs here, and you have to feel for yourself if it's worth it or not. And again, with accessibility, you probably want focus changes, which there's also APIs for it, but it definitely takes a lot more work than just relying on the view system. So again, look at metrics and see, do I really need this? I mean, if you do, it's probably worth it, but look at the metrics first. And again, RTL layouts. This is not specific to drawing, but to use custom drawables, you will have to lay out your drawables manually. You can build abstractions for this, but there's nothing in the Android framework for it. Meaning you can't, I mean, linear layouts and such and relative layouts handle right to left for you. This is something that isn't automatic when laying things out by hand. Another important point is touch events, which the Android view system handles very nicely by delegating to the correct views to handle the correct touch events based on the location. It handles sending action cancel events to views when they are no longer being touched. It handles multi-touching between different views, great. None of this works if you do this approach. So if you need like complex touch handling, again, confining that custom touch handling and pulling that out into a typical view hierarchy might be the sanest solution. But you can always override on touch and perform the touch event handling yourself, at least for the simpler cases. Again, it's something to think about before diving down into this. Drawable state is another one. Like, for example, with a button, probably once a pressed event. This is something you'll need to handle yourself via on-touch and set state on the drawables. Otherwise, this is handled by the view system for you. So again, it's a trade-off. In some cases, it's definitely worth it. In a lot of cases, though, it might not be. So I guess what I'm saying is optimize responsibly. But if you apply this, you can get great wins. Thank you.
Thank you. Any questions?
Again, my name is Emil Pasquale.
Yeah.
If there's no questions,
Yeah.
yes, sir. Just 1 second.
Hello.
Oh.
Test. Okay. In one of the slides, you translated the canvas and then translated it back. Is there a reason why you didn't stash the change and then save the change?
Yeah, so the canvas is shared, right? Because you only have one view. So every time you do something on the canvas, like an operation, a translation or something, you either undo it after, or you can actually, Canvas has other APIs, like you can do Canvas save, do your stuff, and then you do Canvas restore.
Yeah,
but I mean, in that case, it was just a simple translation, so I mean, you might just as well translate it back. It doesn't really change anything.
Short answer, there's no real reason, I guess.
Okay, thanks.
Anybody else have a question they want to ask? Cool.
Okay.
Thank you all.
Thank you.
See ya.